What's going on YouTube? Any second now we should be live. Welcome everybody to my channel. My name is John. Today we're going to be learning about the Fibonacci numbers, and in particular I want to show some amazing facts about the Fibonacci numbers for everyone. So when I say for everyone, I actually mean that. There's going to be something in this video for everyone, I hope. So we're going to be starting from the very beginning, from the ground zero, and then try to work our way up. So I will say it's not for everyone. Some, professional mathematicians might not learn anything new in this one, but I hope that there's still something entertaining about it, if nothing else. And some questions for you all. So I am a new teacher in math. I did a degree in math like 15 years ago, something like that. And now I am rebuilding my skill and love of math teaching here on YouTube. So anyways, let's get started. For everyone, I really mean that we're going to be learning some concepts from grade school. From grade zero, from, learning arithmetic, all the way up to undergraduate mathematics. So we're going to be going from arithmetic and adding numbers all the way up to linear algebra, which is a topic that I love very much, and that's what I'm practicing here primarily on this stream. So let's start. Let's just get started. And over time, people will be rolling into the chat, I hope. How's it going, everybody? Let me know if the audio levels are okay and everything. So these are the numbers that I want to calculate today. We're going to find the 4th Fibonacci number, the 12th, the 23rd, the nth, the 34th, the 123rd, and then question mark at the end. So one thing I want to get out of the way from the very beginning, what is this video not? That's a good question. All right, so what this is not about is, this video is not about gardening. It's not about collecting seashells. It's not about observing baby rabbits. It is not about, what else? I don't know, throwing baseballs. Okay, so these are all lovely applications. Oh, throwing baseballs, it's also not about making money from the stock market. Or lots of other topics. These are all beautiful ways that people have found that you can apply the Fibonacci numbers, but this is not about that. This is actually truly something much more simple and pure in my mind. This is just about the Fibonacci numbers themselves, because they're interesting, because they're kind of cool, because I geek out about them a lot. This is actually just, for lack of a better term, a pure math video. I'm interested in studying this mathematical pattern in and of itself. It doesn't need application to make you money or to learn how far you can throw a baseball or anything like that. This is actually just about some cool number facts. And I wish that people showed me more of this kind of math when I was young. So I think that throughout this video, we will be getting to some applications, actually, of the Fibonacci numbers that a lot of people have never seen, or applications of other math to the Fibonacci numbers, maybe. So let's begin. What are the Fibonacci numbers? I teach kids, and it's very simple. Hey, what's up, Demo Tat? How are you? So I teach kids how to add numbers. Like literally I teach like all the way grade K to 12. I teach K to 12 math a lot. And I just tell them, okay, what's 0 plus 1? 1. What's 1 plus 1? 2. What's 1 plus 2? 3. What's 2 plus 3? 5. What's 3 plus 5? 8. What's 5 plus 8? 13. What's 8 plus 13? 21. What's 13 plus 21? So now we're going to start getting into some bigger numbers, right? Like they're starting to get a little bit harder. But no matter who you are, I want to insist that no matter who you are, at some point this is going to start getting hard. It starts out easy, and we all know 0 plus 1. So the kids love it when I ask them, like, honestly, all right, what's 0 plus 1? And they're like, why are you asking me that? I'm like, no, trust me. All right, now what's 1 plus 1? And they're like, dude, this is still so easy. Why are you asking me that? And then immediately, just without any other explanation, you don't have to describe anything about flowers or anything, or rabbits or anything. Dude, this is already fun. Like, how far can we go and add these numbers in our heads in this sequence? 21 plus 34, 55. At some point, I'm going to get stumped. But 34 plus 55, 89. And now we're going to start getting into 3-digit numbers. Maybe this is a good place to pause. Yo, Demotant, Naman, yo, JC, how are you, man? I'm doing good, dude. Thank you for tuning in to this special stream. So today we are studying the Fibonacci numbers, and we are going to be learning some facts for everyone. And trust me, it actually does connect to linear algebra if you stick with me here. Okay, so level 1, what is the 4th Fibonacci number? So here, I didn't even get too far. I didn't want to explain what I meant by F4 first. What is the 4th Fibonacci number? For reasons that I don't want to go into too much, I want to say that one's F0, this one's F1, F2, F3, and F4. So boom, we've already solved our first problem together. There's the 4th Fibonacci number. F4 is 3. Okay? So we already passed level 1. And I use levels here very deliberately. When I teach kids arithmetic, I like to call this like levels. Like, dude, like it's like a video game. Like, how far can you get? Like, we got to level... I mean, I usually say that this is level 4, you know, and then this next one is going to be level 12. Can we get to level 12? Let's pause for a second. Where am I getting these numbers? Why am I going 4 and then 12 and then I think that the next one that I'm curious about is 23 and then 34. Where am I picking these numbers from? Why am I interested in these? Dude, I like to explain math in ways that have some motivation. Like, where did you get this problem from? Why are we solving this problem in the first place? Who came up with this problem? When am I ever going to use this in the real world? Anytime that I learn a new mathematical concept, I try to see, is there a way that I can study this with the numbers 1, 2, 3, and 4? Can I find some way to use the numbers 1, 2, 3, 4 to make up the problem? So, without even getting too formal or anything here, what were the Fibonacci numbers? We could say add the last two. Really just add the last two. Add the last two numbers, or something, to get the next number. This is a good definition right here. And add the last two numbers. You can go pretty far with this, and I've seen some kids get pretty dang far. So let's try to figure out, what about F12? Can we get to F12? Did we already get F12? I don't even know. I haven't practice this or anything like that. So we got to F4, F5, F6, F7, 8, 9, 10, 11. We just needed one more. So, dude, you can't make this up. I didn't know. This one is actually level 2 because we got to 3-digit numbers. I don't know. I picked the random numbers 1, 2, 3, 4. I have not practiced this part of this live stream lecture. But that's kind of cool. That's like delightful to me. There's just like a delightful surprise that like level 2, these are 3-digit numbers. We start getting to 3-digit numbers. Okay, so 3-digit numbers. Can I still do this in my head? Can I do two-digit numbers in my head? I can do it. And here is where you can start to employ mental math tricks. 55 plus 89. How many is it from 89 to 100? It's 11. 89 is 11 away from 100. So then how much more do you need to add to 100 to add 55 in total? In other words, what is 55 minus 11? It's 44. So this number right here is 144. And this, we just successfully beat level 2. So how far can you go? Pause the video if you want to, and try to calculate as far as you can mentally in your head. Like, how far can you get until you have to start writing them down on paper? So we beat level 2. What about level 3? Okay, oh, yeah. I didn't 100% complete this thought, so let me finish this. 1, 2, 3, 4. So I could ask, whenever I'm trying to come up with examples for myself, I like to use the numbers 1, 2, 3, 4. So what about F4 or F12? F12 is 1 and 2. F23 is 2 and 3. F34, and we could do F45, or we could go to F123. I think that's the next one that I chose. So already, just thinking about it, if we're trying to do these in our heads, I don't think, because these numbers are already getting fairly large. Already. By the 12th number, we're already getting into 3-digit numbers. How far can I go in my head? Can I get 23 in a row in my head? I don't think so, honestly. I really don't think so. Definitely no way could I get 123. Those numbers are going to be pretty big. Okay, so let's keep going. That's why I picked the 12th number, the 23rd number, the 34th number, and then the 123rd number. So how can we get those bigger numbers? We're going to need more tools, more techniques, more math even. I wanted to copy this. Let's copy this over. So we've gotten pretty far so far. We got to F12. Now, I could go a little bit more in my head. Again, adding 89, another way to say this is that 144 plus 89, and I'm trying to do this in my head, is 144 plus 100 minus 11, right? 89 is 100 minus 11, and it's way easier to add 100 than it is to add 80 and 9 or something. So this would be 244 minus 11. This is 233. So the next number is 233. I know that. Let's erase all this scratch work. We could keep going. So that one is F13. F14, the 14th number, 144 plus 233, 377. Pause the video for real, and how far can you go doing these in your head? It's not the worst way to spend 10 minutes. Dude, it's so much better of a hobby to just calculate Fibonacci numbers than scrolling Instagram or YouTube Shorts. Like, try doing some mental math today, like right now. It might have been 20 years since the last time you've done something like this, but it's it's kind of like a Sudoku or something. It's not the worst way to spend some time. 610 plus 377, 987. And again, 987, I see a nice kind of little pattern about that 987 is 1,000 minus 13. So I'm thinking of 987 as 1,000 minus 13 to add for the next one. My colors got out of order. All right, so we got to 987 plus 610 would be 1,610 minus 13, which is 1,597. Dude, at some point, any of us is going to need to go to the column addition method of calculating these numbers, and there's nothing wrong with that. I've practiced these a decent amount, so I, can do some of these in my head, but this is a place to try to learn these types of shortcuts, if you will, or tricks or ways to add numbers. Okay, so 1,597. Again, in my head, I'm doing 1,597 plus 1,000 minus 13. So it's going to be easiest if I do 1,597 minus 13 first, which is 1,584. 1,584 plus 1,000 is 2,584. Cool. 2,584. How can we get to 23 without the column approach? I think right here is where I'm going to surrender, let's say, and say I probably could do that in my head, but at this point, 1,597, 2,584. Let's go to this good old classic way of adding numbers. So I want to show you a couple of ways that we can do this, and you may not have seen the second way. I didn't until later, until I was I don't know, in college or maybe even as a teacher, I forget. But we've all learned this way. 7 plus 4, right? 7 plus 4, here, white needs to be first, because you don't see me rearranging my colors, but whatever. 7 plus 4 is 11. And then here's 18, 11, and 4. 4181. Okay, cool. So 4181, we can write this out. Let me show you another way to do this that I don't think everybody has seen. 1,597 plus 2,584. Y'all, please let me know, how are the audio levels? Can you hear my voice correctly compared to the background music? Do you hear the background music, by the way? Yeah, I think you should be able to. Classic addition. I know. It's still simple, but we're going to get into college level math eventually. We're doing Fibonacci numbers in 7 difficulty levels. And so currently we are trying to get to F23 right now. Okay. This way I did not see until later. I've done it horizontally in the horizontal addition method all the time, but here, you can, when you're doing the column-wise, table algorithm, you can add 2 columns at the same time, and you can do 2-digit numbers. What is 97 plus 84? I'd add 100 and subtract 3, so that's, add 100 and then subtract 3, so that's 181. And then what's 16 plus, Or 15 plus 25. 15 plus 25 is 40, 41. Boom. That was faster because we've practiced so much two-digit addition. Because we've done a bunch of two-digit addition practice in level 2. This method, if you get good at two-digit additions in your head, this is just 2 steps. You know, we did step 1 and then we did step 2 in this practice, in this practice rep. Whereas this took 4 steps. And there's 4 opportunities to make a typo somewhere along the way, right? Okay, so we got 4181 either way. Now let's keep going to find F20. So we're adding the previous 2 numbers, 4181 plus 2584. I'm going to take this method 2 right here to try to make these faster. So 80 plus 80 is 60. So this is, or 80 plus 80 is 160. So this is 165. 42 plus 25 is 67. Right? Dude, that's, I think, faster. 67, 61. 67, 61. There's F20. We're so close. 41, 81 plus 67, 61. Add these two. 142. 42 plus 67. I see 40 plus 60 plus 9, right? 40 plus 60 plus 9 is 109. Just double checking. Yeah, that's correct. 10, 9, 4, 2. 10, 9, 4, 2. Nothing wrong with like pronouncing out loud the numbers as like 1, 2, 3, 4, 5 or 4, 1, 2, 9. For this type of math, it's fine. Hey, Sahid's, how's it going? 67, 65. Oh, did I get it wrong? Oh, it is, dude. Thank you. Why did I get that wrong? Dude, thank you so much. I almost freaking, everything almost fell apart here. Okay, 67, 65. So we need to add 4 to both of these. I'm telling you all, I will make mistakes here on stream. Let's highlight that was a mistake, which is part of the beauty, I think, of a freaking live stream. You know, 10, 9, 4. We added 4 to this, so 6. Oops. And this is a cool opportunity to also mention when I'm teaching kids this way and I'm doing these as well with them, sometimes I'll make a small mistake and it's very humanizing. You kind of said it was 67, 65, then wrote down 1. Exactly. So I call that a typo. I might have said the right number, 65, but I accidentally wrote down the wrong number. And that's why I really love this method of just doing 2 additions when you can. Or 3. Like if you can do 2 3-digit numbers. And it's just like fewer opportunities for typos, for like little mental math errors. Dude, thank you. It's great to have somebody in chat catch an error like that. All right, so, dude, we should be using colors more. Let's call this F21. Bro, thank you so much. So now, F22, we're so close, because we want F23, and then we will be golden. Here, we'll write it here for space. So our goal right now, to beat level, 3, is to find the 23rd Fibonacci number. And by this point, we are doing column additions, right? 10, 9, 4, 6, plus 67, 65, 67, 65. Everybody makes mistakes. That's like something that I love to humanize to my students. Everybody makes mistakes. And it's partly why I like to lecture live like this. Like, real mistakes will come up. It's hard, like, this is how you know I'm not AI. I'm not ChatGPT. Anyways, let's keep going. So, since I've made a mistake somewhere along the way, I want to start slowing down and start doing it a little more like the traditional way. Like, maybe at some point you do want to slow down and make sure you get it right. 11, 17, 11 plus 6 is 17. So it's not obvious that the two-digit additions are faster, the two-column additions. Sometimes they are, sometimes they're not. It's just an option. It's just another option that you can do. Like, we could have tried to do, I feel like this wouldn't be so bad. You could have seen that as 1,000 minus 54. So if you subtracted 54 from 765, you get 714. So that would be... Oh, wait. Okay, I got something wrong there. Anyways, let's... I misspoke somewhere in there, but we're almost there. We're almost there. 17,711. 17,711. And then the final one, F23, to beat level 3, is going to be 17,711 plus 10,942. What I love about this as a practice problem for kids is that this is not beyond like a third grader or a fourth grader or something. They do five-digit additions all the time. You know, they are taught to do 5-digit additions, but those problems are just like out of thin air. They're like completely out of thin air. This is coming up in a real problem that they've solved before. And maybe they've been working on it for months, and now they're finally getting to the higher levels and bigger numbers. And these 5-digit additions are coming up naturally, which is super cool, I think. This one definitely is 53. And then I see 86 and 2. 28653. Boom. 28653 is our wonderful level 3 Fibonacci number. 28653. Let's make sure that I'm still on track. If somebody could double check my things as we go. Let's see, there's and then I like to tell kids that there's like an online, what is it, like, sequence of numbers, OEIS? Yeah, it is OEIS. OEIS, there's a website dedicated to just collecting these lists of numbers, because mathematicians geek out. Like, I geek out about coming up with interesting different lists of numbers. Yeah, wow, are you counting rabbit population growth? No, dude. I wrote it, unfortunately I erased it, but if you rewind, I said, what is this stream not? We are not throwing baseballs anywhere, we are not gardening, and we're not cultivating rabbits. We are just solving math problems for fun. But yeah, thank you. I'm glad that you get the inside joke on that. I'll get to that. I'll get to why we're talking about rabbits. But no, this is just math for math's sake, because math is fun. Adding numbers is fun. No other reason needed. So we are doing Fibonacci numbers for everyone. We've done so far, level 1, we've done level 2, we've done level 3, now we're going to get to level 4. Level 4, actually, I'm going to go to general Fn. So first off, what do I mean by that? Now we can get a little more formal, and I don't shy away from this, dude. Like, from little kids who have practiced this problem and they've gotten used to the notation, or they've gotten used to the idea of Fibonacci numbers, then I just say this like it's no freaking big deal. F0 is 0, F1 is 1, and then forever after that, you add the previous 2 Fibonacci numbers. Like, no big deal. I'm not gonna, like, define this as a scary term, like a recursive sequence, like a recursion or something. This is just my symbols. Like, for example, F2 is the F0 and F1. F3 is the last 2 numbers before it. F4 is F3 plus F2, on and on and on, right? So that's kind of step 1 to level 4. But I actually want to go further than this. This is just like a more formal mathematical description, like writing of the Fibonacci sequence. Now, I want to actually... there's a lot of things that we could do here, but like there are some really cool little simple mathematical identities that you can prove with the Fibonacci numbers, and I should grab my number theory book back there and look up a couple, but the one that's relevant to this stream, yeah, like there's some cool ones, like F2n is XYZ, I forget what they are. Like, I think that there's a cool one about, now that we have this notation, there's something like if you add the odd Fibonacci numbers or something. Let's try this one, because I think that this one is interesting if I remember correctly. Yeah, if I remember correctly, I think that this one is interesting. So we found, so we can create a table here. When n is 1, the Fibonacci number is 1. When n is 3, well, we could write them, right? Like 1, 2, 3, 4, 5, 6, 7. And this can be a way to guide somebody toward making some mathematical discoveries, which are freaking cool. So we have 1 plus 0, 1 plus 1 is 2, 1 plus 2 is 3, 5, 8, and 13. So I think that there's something cool about this one if I remember correctly. Now that we have this notation that we're used to and we're starting to get familiar with of f sub some number, f3 is 2, f5 is 5, and f7 is 13, right? Okay, little kid, what is 1 plus 2 plus 5 plus 13? 8 plus 13 is 21. That's interesting. So let's say, how would I write that in the table? I'm not going to try. Well, this is adding 4 Fibonacci numbers and skip counting as we go. Don't worry too much about this 2n minus 1, but if we add 4 Fibonacci numbers, then we get 21. Okay, wait, what about if we add 3 of them? If we add the first 3 odd Fibonacci numbers, then well, it would be 21 minus 13. 1 plus 2 plus 5 is 8. Ooh, wait. That one also sounds familiar. What is 1 plus 2? So what am I doing here? I did 1 plus 2 plus 5 is 8. What is 1 plus 2? Well, that's 3. Oh my gosh, there's something cool popping up here. I think I see a pattern. That 3 is right there. This 8 is right there. 8 plus 13 is 21. Right? And 21 is down here. So that's actually kind of cool. If you add every other Fibonacci number, I think you got F23 wrong. Did I really? Man, are you serious? I was going to look this up. F23, did I do that addition wrong? 17, 7, 1, 1. Did I copy them wrong? 10, 9, 4. Oh, shoot. Okay. See another typo right here. This was a 4, 6. I think I miswrote it from here. Yeah, the problem is that I recopied that error that I made earlier. So this was supposed to be a 6, and then this one is supposed to... Thank you, dude. Thank you. This one is a 7, right? I think that's the error. 286... We'll see. Is that correct? 28657. There we go. All right, thank you. Thank you for catching me. It was the same error as before. I just recopied it. I didn't fix it in both places. All right, so typos happen. Let's keep going. So here you can start to create and find these patterns that are actually kind of cool. And well, if we add the ninth one, the ninth Fibonacci number would be this next one right here. So it kind of makes sense that if 21 lines up right here, then 21 with whatever this is, right? Then that is going to get the next Fibonacci number. So 13 plus 21 is 34. And 21 plus 34 is 55. Somebody can check for yourself that if you add the ninth Fibonacci number, the ninth one we already did here, 34, and then this would be 21 plus 34, and now that's 55, right? So this pattern holds. And this is a way that you can try to introduce some of these mathematical discoveries, which is freaking cool, I think. And yeah, this has worked for me with kids even. All right, I was actually going to show a different fact for Fn, but I'm actually going to go ahead and do that for this one. F34. All right, well, Fn being... this fact doesn't really help me. Let's add another page and let me show you another fact about an arbitrary Fibonacci number. Fn. Now we're going to get into some slightly more advanced mathematics, but I'm going to teach you as we go with this. I'm going to group these in blocks. And I'm going to group these numbers in blocks of numbers like this. But here, in the top left and bottom right, I'm going to have the previous and the next. So when n is 1, then this would be F2, F1, F1, and F0. And we already figured these out earlier. f0 is 0, f1 is 1, and then 1 plus 0 is 1. What happens when n is 2? F1... wait, no, sorry. So f2 is in these two diagonals, f3 is in the top left diagonal, and f1 is in the bottom right diagonal. Okay, so we've listed our Fibonacci numbers. 1, 2, 3, 5. Let's just remind ourselves and get a little list for a few of them. 13, on and on. Right? This one is F1, F2, F3, F4, F5, F6. I won't need this many, but I just wanted to write some of them out. Then F3 is 2, F2 is 1, and F1 is 1. What about when n is 3? Let's do the next one. So, if you think about it, we're adding the previous and current Fibonacci numbers to get the next Fibonacci number. Because fn minus 1 plus fn equals fn plus 1. We had that formula that we wrote earlier. It's just ever so slightly different. So I can add the bottom two numbers, or the rightmost two, like the second column might be, whichever one you prefer, to get the next diagonal number. So this 2 moves over into those diagonals, and the 1 moves over, and then 1 plus 2 is 3. We can continue this for a while, but why am I doing this? I now want to introduce the idea of multiplying blocks of numbers, which is going to be totally different than what most people have seen before. This is going to be a little unique. What is my favorite example again? 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to come up with an example of multiplying 2 square blocks of numbers. Usually they don't teach you this until linear algebra in college, but I think I can teach a 10-year-old this. The way that you multiply to get the new block of numbers is we're going to multiply a row with a column in a way where we multiply the corresponding numbers 1 times 5 and 2 times 7, and then we add those together. So I have 1 times 5 plus 2 times 7, and that is going to be this top left number. So we'll do that one first. 1 times 5, what is little kid? 2 times 7 is 14. 14 plus 5 is 19, right? And again, this is just an example. Like, these aren't Fibonacci numbers that we're working right now, but yeah. So I'm going to multiply that row 1 times 6 plus 2 times 8. So here, 1 times 6 plus 2 times 8. Let's move on a little quicker, because by now I think that we're mostly, I'm going to start teaching to a higher level. So 2 times 8 is 16. 16 plus 6 is 22. I think that this is not the worst way in the world to define and introduce matrix multiplication. Like, call me crazy, but I think that this is not the worst way in the world to introduce somebody to matrix multiplication. So in your head, and again, this is good for our brains so that we don't get brain rot from too much TikTok and ChatGPT. If we multiply 3 and 5, then add 4 and 7, what's that in your head as quick as you can? I see 28 plus 15. 28 plus 15 is 43? Is that right? 28. I want to make sure I just stop making errors. 28 plus 14 is... No, not 23. Yeah. I thought that sounded... that is 42. 42 is what I meant to say. Yeah. So 20... Why did I say 28? 15. 15, not 14. Okay. Slow down, John. Slow down. Slow down, John. 3 times 5 is 15. 15 plus 28 is now 43. Yeah, 43. Okay. So I think that's what I said the first time. Okay, then finally we are going to multiply that second row with this second column. 18 plus 32. 18 plus 32 is 50. Okay, this is all we need so far. Yeah, this is all we need so far. We could extend this to 3 to 3 by 3, like blocks of 3 numbers or 4 numbers or 10 numbers, but this is all we need for today. Check this out. This is a pretty cool mathematical fact, I think. Let's check this out. If that's true, let's start with a concrete example, F2, F1, F1, and F0. In fact, let's get even more concrete. We're starting with the first block that we already wrote before, F2, F1, F1, F0. And what happens if we multiply it by itself? So we do these multiplications. 1 times 1 plus 1 times 1 is 2. 1 times 1 plus 1 times 0 is 1. 1 plus 0 and 1 plus 0. Hey, wait a minute. This one is familiar. We got that right there. Right? Wait a minute. That is F3, F2, F2, F1. Okay. Well, that's kind of cool. What happens when we multiply that block by itself? Just out of curiosity. 2, 1, 1, 1. So practicing this, we get 4 plus 1 is 5. 2 plus 1 is 3. 2 plus 1 is 3. And 1 plus 1 is 2. Hey, though 2, 3, and 5, those are Fibonacci numbers too, right? 2, 3, and 5, if I write them out again, 0, 1, 1, 2, 3, I want to make sure I don't... Oh wait, no, there's no 4 there. What am I doing? 3, 5. This is F0, F1, F2, 3. This is F3, F4, and F5. So this is, and yeah, like I have never actually tried to teach a kid this, but in theory, I think it could work. At this point, I'm more teaching, I think, high school. So this is definitely Fibonacci numbers at different levels, from grade school to college. And I gotta hurry up if I'm gonna. Yeah, I gotta hurry up. If we're gonna get to the college fact. Okay, so this is F5, F4, F4, and F3. If we shortcut this a bit, if we let A be this block, then this is, what I found was A squared, and then this was A squared times A squared, which, just like in regular arithmetic, this is A to the 4th, right? And then what happens if I have A to the 8th, which is A to the 4th? We found that previous one. A to the 4th times A to the 4th is going to be 5, 3, 3, 2. 5, 3, 3, 2. So, if we keep doing this, then, dude, this would tell us F33, F32, and F31. Dude, our question, our problem that, like, level whatever, level 6? No, this is level 5. Okay, so now, now you believe me, I hope, soon, that raising this matrix to powers will get you Fibonacci numbers in the nth Fibonacci numbers. So if we can find A32, this will be the block of numbers F33, F32, F32, and F31. Then, after we find that block of numbers, then F34 is the previous two Fibonacci numbers added together. And we can find this by doing this doubling kind of process, or this exponential, actually. Hey, what's up, Heidi? Good to see you. Yeah, at some point, the idea here is I'm going to lose everybody at some point. I mean, not everybody, not mathematicians, but the point is that this is Fibonacci numbers from level 1 to level 7. Most people are going to drop off at some point. But we've gotten pretty far so far. We've knocked through level 1, 2, 3, 4. And Heidi, I think that you'll really like this video, so I hope you check it out from the beginning later. So here, A to the 8th, this is going to be 25 plus 9. 25 plus 9 is 34. I remember that is a Fibonacci number. And then 15 plus 6. 15 plus 6 is 21. And 6 plus 4. Wait, no, 9 plus 4 is 13. That's what I meant to say. In fact, we already wrote a bunch of them earlier. We even got to F16. We wrote a bunch of these already. So, I'm just spitballing right now. We could write down F15, F16, and F17 and copy that work, or we could do another matrix multiplication. Either way, let's do it both ways. We should see that this is the same. A16 is going to be a to the 8th times a to the 8th, which is this last block that we just found. 34, 21, 21, and 13 squared. And now we're going to start getting some really cool mental math problems for multiplication. So this can get us some multiplication problems too. 21 and 13. Let's have our helpful diagrams. 34, 21, and 21. So I am multiplying these numbers together. 34 times 34 challenge would be to try to get used to multiplying these in your head too, but for sake of time and trying not to make mistakes along the way, I'm going to do it kind of the standard way. 12, 9, 10, here 56 and 11. 1156. Just making sure that is... No, wait, what? Oh, yeah, because this is not necessarily a Fibonacci number. It's 1156 plus 21 times 21. That's 420 plus 42, which is 462. 462. Let's make sure that I did it right, just so I don't make mistakes. 400. Wait, did I mess up? Okay, I did do my multiplication wrong. 2, 0, 2, 4, 440. Where did I get? Slow down. 1 times 1 is 1. 2 times 1. 0. 1 times 2. 2 times 2. Okay. 41. 441. See? It's good to double check yourself. It's good to practice and try to do mental math stuff. And, like, don't just freaking reach for ChatGPT and a calculator, like, every chance you get. That's, like, super lame. 56 plus 41 is 97. And 11 plus 4 is 15. 1597, I remember, is a Fibonacci number. So, dude, 1597, and I'm just going to take the shortcut. You can use that approach to get 987 here. Show that matches these additions, 987, and 610. Should be right there. Then, we have not gone beyond those numbers, or much farther beyond those numbers. Let's find the 32nd Fibonacci number a little faster than before. So, A32 is going to be A16 times A16, which is, as I just said, let's just yoink this. Erase here, paste, move, paste. Okay. Now, it's a little tricky, but again, multiplying 4-digit numbers is not beyond us. It's not beyond a 5th grader. Like, somebody can do 1597 times 1597. I'm not going to be able to get to the to the meat of this video in time. I'm running out of time. 1597. I'll have to try this again in the future because I want a self-contained video. 1597 times 1597 is a huge number, relatively. 409. 550. I forgot that I have a thing, and I don't, yeah, I forgot that I don't have quite as much time as I planned on. 2550409. Haha! Look at that number. That's great. That's a great number. It's huge. And now we're going to do 987 times 987. So we've got 987 times 987, and then we're going to add these two. Again, just for sake of time, I'm going to cheat with a calculator, but trust me, I can do these, especially if I'm not live on the internet. So practice this. Like, it's not the worst way to spend 5 minutes to try to actually have some multiplication problems, and it's so simple too. Ooh, yeah, what's the shortcut, Shori? Yeah, let me know. What is the shortcut? So you'll find, figure this out for yourself, that would be 974,169, and then we want to add that. Nope. We want to add that number to this number. And we could do it freaking by hand. Let's do it. 78. Sometimes it's just faster to do it, 45, 152, 152, and 3. So again, I was using those like 2-digit additions. Let's just double check ourselves. 1597 squared. 3524 578. Yep, got it. So this is using matrix multiplication. I found that the 33rd Fibonacci number is this. And doing this by hand would take a while, like if you do it the regular way, right? Because these numbers are getting big, right? And then so I showed matrix multiplication for first column. Now I'm going to use the calculator just to get this one. 1597, again, just because of sake of time, times 987 plus 987 times 610. So this entry that I just described is 21,309. Cool. 21,78309, and then plus 3. Oh, right. This one again was the 33rd Fibonacci number. I don't even need to finish the matrix calculation for the rest. And then this one was F32. So then, to answer our question about F34, this is F33 plus F32. I guess my accent color was supposed to be green, but adding these numbers together, we get 3524578. 3524578. This number to beat level whatever we're on, 5702887. This is the 34th Fibonacci number. Boom. Look at that. Carey Hamilton theorem, sir. I've never heard of that. Okay, now we can continue doing that in this approach. And it would work, right? A64, we already found 32nd, you know, and then we could go one more. So we could do the same approach as last time, but the problem here is that this is going to, there's just a lot more room for error, especially if you're doing this without a calculator. Multiplying these numbers by themselves is going to start getting really big, really big. So I'm going to leave this video, unfortunately, on a cliffhanger. And next time, we are going to show an approximation formula. I'm going to find an approximation formula for large Fibonacci numbers. And we're going to do this, and this is college level math. I've done this a few times on stream. Sometimes I get it right, sometimes I get it wrong. I think next time, I think we'll be able to get it. And I'll probably just edit this video with the next one and upload this as a separate standalone video. Thanks everybody for watching. TLDR, what we'll see is that we can use this matrix and we can find something called the eigenvalue eigenvector pairs. And using this, we can use the eigenvectors to calculate large powers of a matrix. And we'll see that this is something. We'll figure out what this means next time. So, and then that will give us a good approximation for large Fibonacci numbers. Thank you for watching. Yeah, please like and subscribe. Also notice that if we did find 128, then we need to go backwards with the old approach and do subtractions, and subtractions are hard. So anyways, even if you could do it this way, even if you did do the matrix squaring process, like, I don't know, at some point, like F1, 2, 3, 4, 5, 6, like that, at some point, using a formula, if you can use a formula, and if you can find a formula, then it's going to be worth it, right? 1 minute. Let me take a break. I think I actually do have time for this at the end. Actually, I do think that I have time for this. Let me take a very short break. Hell yeah. Okay, hell yeah. I do still have time. Let's go. So, level 7, F question mark, we'll do that later, if we can get to it. Level 6, let's find any giant Fibonacci number like this. Like, the numbers, just imagine how big these numbers are getting. These numbers are getting huge. They're already 7-digit numbers for F33. Dude, what is F128? Or not F128, but F123. What is that gonna be like? Again, why am I choosing 1, 2, 3? It's because I love the numbers 1, 2, 3, 4, and I like to make up my own math problems for myself when I can. So let's make up this math problem where we want to find the 123rd Fibonacci number. You could do it the way that we were doing before, but there's just like a lot of opportunity for typos here. So I'm going to show a new mathematical concept. And now we're reaching into college level math. And this is kind of cool. I think a high schooler could learn this, and just like specifically for Fibonacci numbers, and we'll learn some concepts along the way. So what we found, what we showed already, was that this matrix is really powerful. A to the k is going to be fk plus 1, fk, fk, and fk minus 1. So if we can find a nice approximation or a nice formula to calculate a to the k, then if we can find a nice formula, then we'll have a nice way to calculate this large matrix, or this high-powered matrix. Okay, so what does this mean? So in linear algebra, which we've seen my streams, I think that this is in chapter 5. In my chapter 5 videos, you'll see me working this problem a couple of times. I believe that this is 5.3 in this wonderful book by Frale and Beauregard. It's like an applications of eigenvalues and eigenvectors. Yep, I was right. Look at that. This shows up in section 5.3. So if you all want to see all the details, you can go to some of those videos and you can see me stumbling on this problem a few times. I've done it a few times, including privately. I think I'll be able to get it well this time. We know, or instead of saying, like, at this point, I will start using more technical terminology and whatnot. Theorem, if A is a square matrix with non-zero determinant, then A I think that this is right. I hope that there's not other conditions that I'm forgetting, but I think in general, an n by n matrix that is invertible with non-zero determinant, A has n eigenvalue, eigenvector pairs, lambda I, vi, and these are not necessarily distinct, by the way. They can be repeated in this process. You might have the same eigenvalue, eigenvector twice in some cases. So not necessarily distinct, such that a matrix times this special vector is equal to just a stretching or shrinking of that same vector. So this is a really useful theorem. This is something, when we say theorem in math, we're talking about mathematical facts that require a proof, but we know that this will always be true. Correct me in the comments if I missed a detail. I'm going to call that theorem 1, and then I'm going to call this one theorem 2. And I'll switch the color just for fun. Theorem 2. Let's see. A matrix A with eigenvalue, eigenvectors, can be diagonalized. So what does diagonalization mean? D equals C inverse AC, where C is a matrix of the eigenvectors, and D is a matrix with the eigenvalues. Lambda 1, lambda 2, ... lambda n. And then zeros everywhere else. Somebody asked in the chat if this was conjugation. Yeah, it's exactly like conjugation is kind of a more general concept in math of formulas kind of this form. When something is, multiplied by an inverse and then multiplied by the thing on the other side. I'm having a hard time describing that a little more formally, but this is like an example of conjugation. Yes, absolutely. How large in terms of megabytes is your math notes file? That's a good question. I have no idea about megabytes, but we have 478 pages. We have 478 pages in this giant linear algebra notability file. Okay, so if you believe these two facts, which I'm going to omit the proofs today, I'm not going to try to prove those. Then, using theorem 2, D equals C inverse AC, this implies if you multiply both sides by C and then multiply both sides by C inverse, then A is equal to CD C inverse. So A to the K is equal to CD C inverse. And I'm going to write it like this. So we have K of them. CD C inverse, CD C inverse, CD C inverse. K times, right? Well, if we rearrange our parentheses, which we're allowed to do in matrix multiplication, we could see that if we rearrange our multiplications, it's called associativity, then, dude, check this out. This C inverse and that C inverse cancel out. And we get D, C inverse C, ... C inverse C, D, C inverse. Then this is C, D, I, D, I, dot, 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 I, D, C inverse. So just like in the real numbers, where 2 inverse times 2 is 1/2 times 2 is 1, in the world of matrices, an inverse matrix times a matrix is the equivalent of 1. In matrices is the identity matrix. So the identity matrix has this great property that you would want of any identity in different types of math, in different algebras. The identity times any matrix is A. Just like in the real numbers, 1 times any number is A. So that's why we call it an identity. It preserves the identity, like when you multiply it by a thing, just like the number 1 in regular numbers. So then if you believe that, then, well, all those i's just kind of disappear, or like they disappear, the one that multiplying by 1 does, and then we have k d's and then a c inverse on the right. Cool? So now that's a useful bit. We've made some progress. Further, I will say D, which I defined as this special matrix that's what we call diagonal. This is a diagonal matrix, which means it has entries along this main diagonal and zeros everywhere else. You can show for yourself that d to the k, when you multiply like a row, for example, lambda 1, 0, dot, 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 0, if this is the first row, and then you multiply it by the column, lambda 1, 0, dot, 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 0, like when you do these matrix multiplications, this is ultimately going to be lambda 1 to the k, lambda 2 to the k, dot, 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 lambda n to the k. So, a to the k equals c d to the k, c inverse, is, I'm going to say, relatively easy. This is somewhat simpler because d to the k is, like, we can write that down, and c, we can also write down what c is. C will be a, I claim that C is going to be this matrix of 2 columns with 2 eigenvectors. So we're getting close. We're getting close. This is the fact that we will use to get to our approximation formula. We now compute. We find these like regular numbers, lambda I, and these vectors, vi, for our Fibonacci matrix. 1, 1, 1, 0. They satisfy, the definition of these things is such that a times vi is equal to lambda I. What does that mean? Let's pause for just a second here, because I think I have the time for this. If I have a vector vi, then what we're saying is that when we multiply that vector by the matrix, it is just a stretching of that vector. Or, to be a little more precise, it's a scaling of that vector. It will still lie on the same line it will still have the same angle theta that it originally had, but it's just stretched or shrunk or reflected, but it still lies along the same line. We will see that we will find two different eigenvectors, v1 and v2, and I'm making up the directions on them, but maybe v1 is stretched like that, maybe v2 is shrunk and reflected, maybe. I don't know. But the important thing is that these eigenvectors are going to kind of have the same direction. They still lay in the same line, the same subspace of the plane. So then, this is the important formula, right? These exist. Then AVI minus lambda I equals 0. So A minus lambda times the identity matrix. Oh wait, oops, I missed the vector VI there. Whatever, yeah, you see that. If the vector is not, if it's not the 0 vector, then, which would not be interesting, what's interesting is that these are non-zero vectors that can be stretched, or stay in the same subspace. Since VI is not 0, then we know that the determinant of A minus lambda I, or minus lambda times capital I, should be equal to 0. I won't fill in the details right on that. I want to move on. Let's remember that our matrix A is this, so A minus lambda I is going to be 1 minus lambda, 1, 1, and minus lambda. And if you use vertical bars like this, this is another way of saying determinant. What is the determinant of a 2x2 matrix? Let's pause and say what that is. The determinant of a matrix, of a 2x2 matrix, which is all we need today, is defined as AD minus BC. AD minus BC. I see it as that negative slope, subtract the positive slope. So then, if that's true, then this determinant is 1 minus lambda times negative lambda minus 1. This, if you factor that through, we can see that that's lambda squared minus lambda minus 1. Let's add a page. Oops. Add a page. Let's add another page already, because I know I'm going to need it. Since the determinant, remember that we're saying that the determinant of A minus lambda I is 0, then lambda squared minus lambda minus 1 equals 0. And we can solve with the quadratic equation. Back to the idea of teaching this stuff to anybody. If I had a motivated high schooler who I was private tutoring, because man, I wish that they would teach this sort of thing in a high school classroom, but they wouldn't. If I was private tutoring somebody and trying to motivate like the quadratic equation, I don't think it's a crazy idea to show this example and like omit details. Don't fill in all the details, but say like, oh, I was working a problem the other day that looked like this. Like solve this quadratic equation. Dude, the quadratic equation does pop up, you know? It pops up in other math all the time, and it probably shows up like if you're like throwing baseballs and seeing how far you can throw a baseball or something. X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So this is 1 plus or minus square root of 5 over 2. I'm going to let lambda 1 be the smaller one and lambda 2 be the bigger one. We find v1 and v2. These are the eigenvectors corresponding to these eigenvalues. Again, they're the special vectors that will just be stretched to, or stretched or shrunk or stay on the same line. But they're these special vectors that make a lot of math problems easier. We have the equation a v1 equals lambda 1 v1. So this corresponds to the equation 1 1 1 0 v1 minus lambda v1 equals 0. 1 minus lambda 1, 1, 1, negative lambda 1 times v1 equals 0. This corresponds to solutions of if we say that v1 is xy, just temporarily, we have x minus lambda 1 times y equals 0. If you've learned about computing eigenvectors, you know that these two rows have to be a multiple of each other. Like if you multiply the second row times 1 minus lambda 1, you would see that if you multiply the second row by 1 minus lambda 1, then we'll see that negative lambda 1 times 1 minus lambda 1 is equal to negative lambda 1 plus lambda 1 squared. And from what we remember before, these equations satisfied this. Lambda squared minus lambda minus 1 equals 0. That looks quite similar to this thing. If I rearrange, lambda squared minus lambda equals positive 1. So this thing is positive 1. This is lambda 1 squared minus lambda 1, and that should equal positive 1. So the second line is equivalent to the first. If I were trying to explain even further to a curious kid or something, linear algebra is an extension of the idea of solving two linear equations. Like if we have two different linear equations, two different lines, finding the solution of those two lines is a problem that we've all solved in regular algebra. But then sometimes your two lines are the same dang line. Like sometimes you have just two different ways to write the same line. Like x plus 2y equals 3 is the same as 2x plus 4y equals 6. The second line, the second equation is just the first equation doubled. So there's infinitely many solutions in this. Infinite solutions to this system of equations. That is the situation that we have over here. We have an infinite number of solutions to this. So, we could say that x is equal to lambda 1 y for any y. Let y equal 1, then x is equal to lambda 1. And if I want to remind myself what lambda 1 is, it's this concrete number. It is this exact number, but I actually think that this argument is cleaner if we just stay with lambda 1s in various places. Like, instead of dealing with the root 5s and divided by 2 and all sorts of stuff like that, what I just showed was that v1, I said that let y be 1, then x is lambda 1. Like, it's just a little bit cleaner to just keep it with the little symbol that means lambda 1 is this. Similarly, we get AV2 equals lambda 2 V2. Therefore, 1 minus lambda 2, 1, 1, negative lambda 2. This is a way that in linear algebra you learn that you solve systems of equations. Corresponds to solutions of, I see it, I like to use that second line. X minus lambda 2y equals 0. Then our second eigenvector is going to be x is lambda 2 times y, whatever y is. If you add lambda 2y to both sides, x is lambda 2y. So if we pick y is 1, if we pick y equals 1, then we get this nice little equation. So let's go back to our goal. Why are we finding these things again? It's because these matrices will be nice to work with. So I found a vector I found vectors that correspond to these eigenvalues. Eigenvector 1 is here, lambda 1, 1. And vector 2, eigenvector 2 is lambda 2, 1. D is lambda 1 and lambda 2. And remember that these are concrete numbers. These are no longer variables. Like we've solved that lambda 1 is 1 minus square root 5 over 2, and lambda 2 is 1 plus square root 5 over 2. A to the k is, we had CD to the k, C inverse. How do we find, what is this? What is the inverse of an arbitrary matrix? Well, you can do that. You can find that in a few ways. You can do this row reduction process until you row reduce to I C inverse. This is one way. Oh, I had space. Whoops. Let's just rewrite that. Okay. So you can do a row reduction and then get to C inverse this way. This is called Gauss-Jordan row reduction or something. Or for a 2x2 case, we have a nice explicit formula that the inverse of a matrix ABCD is 1 over AD minus BC. This is the determinant, or sometimes written delta. You can show for yourself that this will work. DA negative B negative C. So this is a nice little fact to use here, because and we don't, I mean, there are explicit formulas for a 3x3 and others, but they get really, really ugly, really messy, really fast. So in our case, A to the K, in our case, we were working with 2x2 matrices, so this isn't so bad. A to the K will be this matrix, lambda 1, 1, lambda 2, 1, times lambda 1 to the K, lambda 2 to the K, 0, 0, times the matrix, I'm going to write it as, with parentheses to be clear, 1 over, what is the determinant here? Lambda 1 minus lambda 2. Times, you swap the diagonals, the negative diagonals, 1 and lambda 1, and then you write the negatives of the other two. Negative lambda 2, negative 1. You might ask why that works. Good question. I don't know a very good way to show that from first principles, but if you try multiplying this times any matrix ABCD, you will see, you can show for yourself that 1 over AD minus BC, D minus B negative C, A, times any matrix using matrix multiplication, which we defined earlier. If you try this matrix multiplication, you will get 1, 0, 0, 1, and then therefore this is an inverse of the matrix. It's another math fact that there's exactly one inverse, but we're going to skip that for right now. So we can rearrange the scalar, 1 over lambda 1 minus lambda 2. We have lambda 1, lambda 2, 1, 1, lambda 1 to the k, 0, 0, lambda 2 to the k, and this last matrix is 1, negative lambda 2, negative 1, lambda 1. So it might start looking a little messy right now, but I really do think that this is cleaner, honestly, than doing it with the concrete numbers 1 plus root 5 divided by 2 and stuff like that. But maybe that's just because I'm used to math. I like math. We can multiply matrices in different orders. I think I still want to multiply the second and third first. I usually think of multiplying the last two first. And hey, what's up, Leo Lectures? Dude, Fibonacci. As another exercise, you can try doing this with Lucas numbers or other Pisat numbers. I don't know other Pisat numbers, but I was thinking I considered introducing the Lucas numbers back in level 4 or something that we did earlier. I don't know if you saw the thumbnail, but we're doing Fibonacci numbers for everyone. Fibonacci numbers in multiple different levels for everyone. We're currently in level 6. We've done level 5. We've done level 4. And we're currently on level 6 right now. So we started out defining the Fibonacci numbers, figuring out what F4 is. Then we figured out what F12 was, which is just like, let's start practicing some mental math and we got all the way to a 3-digit number. Level 3, we just keep doing that, and it starts to get to the point where I had to go to column additions. And I even made a typo. I even made a mistake along the way. So there we found F23. Then I introduced the recursive definition. What is Fn for any n? And so I wrote down what the recursive definition would be, and then I showed one interesting fact about the Fibonacci numbers. If you add every other Fibonacci number together with the odd indices, then you get, which one is this exactly? I think that this is F2n, is that right? I forget. 1, 2, 3, 4, 5. Yeah. If you add the first 5 Fibonacci numbers, or skip counting, yeah, I don't want to get too much into the summation formalism and whatnot, but if you add every other Fibonacci number and you add 5 of them, then you get, in this case, you get F10. So I thought about using Lucas numbers here, and yes, you could do all of this. You could do this entire exercise with Lucas numbers. I like to call Lucas numbers like the evil twin of Fibonacci or something. But this is one mathematical fact that we can see a pattern about arbitrary Fibonacci numbers. And then I showed that this matrix actually turns out to work. So I introduced what matrix multiplication, how that works for 2x2 matrices. And we started using that to find powers to get all the way up to A32 to find the 32nd and 33rd Fibonacci numbers, doing matrix multiplications to get these bad boys. So this is F32 and F33, and our goal was to find F34. We found F33 and F32, so we could add those two together, and we solved level 5. Level 6, right now, we're currently finding the 123rd Fibonacci number. We could continue... Yeah, dude, heck yeah, that sounds really interesting. All right, so we could do a couple more applications of this squaring, but the numbers are getting huge and my calculator is broken. So I want to find something a little smarter. So, I mean, I've just been making typos a couple times during this stream. So now we are finding an approximation for any large Fibonacci number. 128, I'm going to say, is a pretty big number. I think that we're going to find a formula that turns out to work well enough. And now we're getting into college level math. I wrote down a couple of theorems. We know what a square matrix is. I claim that a square matrix with non-zero determinant has n eigenvalue eigenvector pairs. What does that mean? They're special solutions of this form. And if a matrix has a set of eigenvalue eigenvectors, we have this special formula, where the eigenvectors are columns of C and the eigenvalues are diagonal entries of D. Then, if somebody believes me, despite the fact that I skipped the proofs, then we would know that D is C inverse AC, multiply both sides by C, multiply both sides by C inverse. We get A, and then we can raise A to the kth power, and we get a nice telescoping property to where A is C D to the K C inverse. So I'm recapping what we've done so far. So this is a relatively easy matrix calculation. And now we are doing this matrix calculation. We, instead of squaring again and again, I'm finding for any Fibonacci numbers, we're going to get to this. We're at a to the k equals these matrices multiplied together. Okay, so again, multiply this and this, add this and this, multiplied together. So this is lambda 1 to the k, and you can see for yourself that we get negative lambda 2 lambda 1 to the k here. We get 0 negative lambda 2 to the k, and we have lambda 1 lambda 2 to the k. Now, doing these multiplied together, let's pause and be clever about this. This is a raised to the kth power. What we want to find is a formula for fk, and we know that a to the k, recall that a to the k is f, the next Fibonacci number, the current Fibonacci number, the current Fibonacci number, and the previous Fibonacci number here. So I don't need to calculate everything. I could either calculate this one or this one. I'm actually going to go with this one, with the blue bottom left. It looks a little easier for me to multiply ones times some stuff, as opposed to lambda 1, lambda 2 times this stuff. And I'm going to skip the others. It doesn't matter what those are. I just want to know what fk is. I don't need to know what the next or previous Fibonacci numbers are. So, multiplying those, we get lambda 1 to the k minus lambda 2 to the k. And then, therefore, the kth Fibonacci number is 1 over lambda 1 minus lambda 2 times lambda 1 to the k minus lambda 2 to the k. And this is an exact formula for the kth. Are you the Leo Alcock, Leo, sir? Yes, that is the Leo. What's up? That's funny. Why do you say secretly Fibonacci is the evil twin of Lucas? Because I always say Lucas is the evil twin of Fibonacci. I like that. You can check relations mod random numbers, and if it's right, you'll probably find a witness of it being mod some number. That sounds pretty cool. Those sound like some pretty cool math facts that you're dropping right there. Okay, so I think that this cleaned up actually the proof quite a bit, rather than dealing with like writing square roots of 5 everywhere. I really think that keeping it in the variables actually helped here. Now let's get to this last final pièce de résistance or something. Let's remember what lambda 1 is. 1 minus square root of 5 over 2. And lambda 2 is 1 plus square root of 5 over 2. So I could substitute both of those numbers in. First, let's see, what is lambda 1 minus lambda 2? Well, if you look at that for a second, well, yeah, like we're going to have a 1/2 minus 1/2, and we're going to have negative root 5 over 2 minus root 5 over 2. It's negative 2 root 5 over 2. So that is just negative root 5. So this formula is already cleaned up a little bit. Where do I want to... Let's rearrange. Let's move some things over. I didn't mean to shrink it, but that actually is kind of nice. So here we have a negative 1 over root 5. And the exact formula for the kth Fibonacci number is 1 minus square root of 5 over 2 to the k minus 1 plus square root of 5 over 2 to the k. This is the exact formula for the kth Fibonacci number. We could ask ChatGPT to calculate this. For our goal in this problem was to solve F123, and we could ask ChatGPT to calculate this and trust that it won't make any typos along the way. But sometimes it can't count the number of R's in the word strawberry, so I'm going to instead continue and try to think a little harder about this. Well, if k is large, notice that lambda 1, which is 1 minus root 5 over 2, if you think about that, that is going to be, well, square root of 5 is just like a little bit bigger than 2, right? So this is like kind of like 1/2 minus 2 over 2, which is like somewhere around negative 1/2, right? Well, what happens if you raise negative 1/2 to a large number? If we raise that to 123, well, actually that's going to be about 0. Because the norm of lambda 1 is less than 1, lambda 1 to the k, when k is large, is approximately 0. It's going to tend to 0 as k gets big, becomes a large number. So, our famous formula is the approximation that this term disappears. We just like treat that like 0, because if k is big, then that term is going to approximate 0. Then what we have left is 1 over square root of 5 times 1 plus square root of 5 over 2 raised to the kth power. This is our famous formula for Fibonacci numbers. What color? I use blue. This is just a little too OCD right now, but level 6 I said is blue, so here we go. This is our famous formula. So we can use that formula to find an approximation. We're gonna guess that it's the closest number to this. 1 over square root of 5 times 1 plus square root of 5 over 2 raised to 123. Okay, so I'm not going to do that one by hand. I was practicing like pen and paper math earlier. Dude, no, we're not going to do this one by hand. But 1 plus square root of 5 divided by 2. I could do it on my iPad, but whatever, let's do it. Yeah. Why don't we try to be fancy here? I have my calculator ready, don't I? Okay, so we have shoot. No. I'm just gonna type it out. 1 plus square root of 5 divided by 2 raised to 123 and then divided by square root of 5. Geez, I don't think that's a correct number. Oh my gosh. All right. No, that is probably correct. I mean, I didn't actually try, like, looking at what this is. This is about 2.26... Somebody check me on this, because my calculator skills are failing me. About 2.2698... I'm going to leave it like that. Times 10 to the 25th. So I thought that I might be able to actually write this down. I guess in the list, in this famous website with many lists of numbers, how do I find, they must have this. What? There must be more. Dude, does OEIS not list like as many as you want? I thought that, what? Does it only list like the first few? Oh, I thought that OEIS would. What is the 123rd Fibonacci number? I haven't tried this yet. Yeah, okay, hell yeah. I just want to see it. I just want to see it for a second. It's very satisfying. And we can see that our calculation is correct. So, if you want to know, you can also just ask Google, always. 22698 374 052 052 006 863. We're running out of space. Eight 956 956 975 682. I've never actually looked at the value of this thing, but then there you go, dude. That is level 6 of the Fibonacci numbers. The 123rd Fibonacci number is right here. If we're using a calculator, why not use an algorithm to compute it? Well, oh, take care, Leo. Take care, dude. Take care. Yeah. So, yeah, look at that. And I found it, I proved this formula. The thing is that an algorithm would be worse than finding this explicit formula. So, y'all, this has been such a pleasure. I gotta go in just like 1 minute. Level 7, just to finish this real quick. Level 7, where else can you find the Fibonacci numbers? There are applications of Fibonacci numbers to more and more advanced types of math. You can find them in nature, supposedly, but what is so cool to me is that the Fibonacci numbers actually were defined as a mathematical puzzle. Just like how this video, like the whole point of this whole video here today was just, Fibonacci is just like a fun little math puzzle. Like, just to come up with big numbers and to practice addition. That is how the Fibonacci numbers were invented. If you want to learn more about this, there's an excellent brand new video from Fibs. I don't even know if that's how it's pronounced. Check out this video. It's amazing. I hope that she does not see this video as Fibonacci slop, because I don't think that this video is Fibonacci slop. This is a great video. I highly recommend it. It's out of control. She goes into the history of the Fibonacci numbers, how they were defined as a mathematical puzzle to demonstrate how the Hindu-Arabic numeral system was better than the Roman numeral system for hand calculations. And she goes into some of the real applications of Fibonacci numbers that are actually like quite cool. Things like Fibonacci heaps are very useful, I know, in programming. But dude, I don't care. I literally don't care. I just care about pure math. I care about these puzzles. And I just wanted to show you all some real math in my mind today. And we went through the Fibonacci numbers in 7 different levels today for 7 different frickin' levels of people. So try it for yourself. How far can you get? Thank you for watching. And yeah, check out, you do follow her, Heidi. That's awesome. It's an excellent video. Definitely highly recommend it. Thank you everybody for watching. This was a pleasure. And yeah, I'll get you the PDF of this sometime, Shori. Yeah, for sure. All right, bye. I gotta go. I am late. Bye. Bye.